Okay. CS103, this is Davina. Please do not swear. Um, okay. So what I can do, but the trouble is it won't show up on the recording, so maybe I'll figure out what to do about that later. I told you at the induction meeting that this is basically a mathematics module, but I also told you that my base assumption is that uh, your school mathematics teachers put you off mathematics for life. Um, so I'm not going to rely on anything they've taught you. I'm going to start again. And let me stick this document camera on. And sadly, this is all going to not be on the Zoom recording because I've had a technology fail. But I will have to make a video of the
They can try to install Zoom, but it'll be in time.
Okay, so we're going to start from nothing, and I'm going to symbolize nothing with a lemon. We're going to learn how to cook numbers, starting with nothing. The lemon represents nothing. Why do I even bother with a lemon? It's important to be able to tell that there is a number and that it's zero, as opposed to just the absence of anything at all. So I'm choosing to use a lemon to symbolize the number 0. And then if I have a number and I want to make a slightly larger number, I can attach a potato to the number to make it 1 bigger. So that spud lemon represents the number 1. And then I can do it again. I attach another potato. Always attach things to the outermost blob. So that spud lemon encodes the number 2. So what I'm saying is numbers are made by counting, and I'm just building models with random veg I picked up in the shop this morning to symbolize the outcome of counting. Okay, so let's go as far as, let's go 3, and let's scale the giddy heights of 4. So it's basically an instant kebab. Okay, now, what makes this a number? That it was built up by counting. And what can you do with a number? How do you compute with numbers? Well, straightforwardly, you're always holding on at the outermost blob, and you're allowed to ask, is it a spud or a lemon? So this one's a spud. So that's the key computational mechanism, is just to ask, is it a spud or a lemon? Are we at 0 or we still got some way to go? If it's a spud, you're allowed to walk along the cocktail stick to the next thing. So if you start with 5, or start with 4, you find out that yes, it's not 0, so you can take 1 away, and you can get to 3. You can take another 1 away, get to 2. Take another 1 away, get to 1, and then you get down to 0. So this is the real thing that makes numbers, is that when you walk along the cocktail sticks, you eventually get to the lemon. Now, this may seem like a strange way of putting it, but the point is that counting down is a process that eventually stops. So that's going to enable us to make computational methods that actually work. That's going to be the explanation of how the process actually does something. Okay, but it's not particularly practical compute. I mean, we'll have fun computing with spuds and lemons, but let's see what we do corresponding to this with computer. And this is where I'm going to get.
You see that the potatoes and lemons are much more intuitive, but let's...
Yes. Okay, so let's go to the PC. And so you're up, Clemens.
I'm up, okay.
I want you so this subsystem of marks is called ask, and it's a system that enables you to write programs and do proofs. And Clemens has never used it before in his life, so I've got to teach him as well as you. Okay, so one important thing about ask is that it starts off knowing nothing. So most programming languages you encounter will have all sorts of built-in goodies. They'll already have some notion of what a number is, and they'll be able to do all sorts of arithmetic. Ask is extremely primitive. It wakes up in the morning knowing absolutely sod all. So we've got to teach it what numbers are, and that's what Clemens is about to do.
Let's see what we can do indeed. So let's scroll down to the ask box.
Yes. And you click in the ask box.
Indeed. And here we want to now say what a number is.
Yes.
And so agree that it's a lemon. No.
Yeah. So when you have, so the data is a keyword, which means I'm inventing a new kind of data. And then we give a name to that, that's number. And then we say, what are the ways of making a number? And we're going to have a capital Z for 0, because that's really the lemon, yeah? And a pipe that means or, and then capital S and number. Yes. And then you hit send.
Yeah, the send button.
Yeah, because ask runs on the server. Ask is happy, and you can hit accept even though nothing has changed. Okay, so we need to learn to read. I know that you have not you've never seen this before in your life, so you need to make sense of it, and that doesn't happen automatically. So, reading ask, step 1. Capital versus lowercase letters are really important. So, any word that begins with a capital letter is the name of a thing. And it just means itself. It's like a proper noun. I'm Conor. This is Clemens. We are us. We're not the same. I'm not a placeholder for something else. I'm just me. So here, number is the name of a type of thing, and Z is the name of a number. It's the lemon, effectively. That's the Z for 0. And S for spud or for successor makes a new number by wrapping around an old one. So I'm saying every number is either 0 or it is the successor of a number. Okay?
So if I would remove the number here, you would have just 2 elements.
Yes, there would just be
S. So
Z and S. So yeah, so this is a way, this allows us to make all the counting numbers. This basically allows us to count, right? You can start with Z and you can build up by adding more S's. So do you think you could get as far as defining 4?
4 is tricky though.
Yeah. I mean, we've got a model of it here on the desk.
So define 4. So am I now allowed to write just equals?
Yes.
Excellent. Good. Yes. Okay.
So
now it seems to be easy, right, to define a number. So one number would be just 0, but sadly Conor is not happy with a 0 because Conor wants a 4 in it.
Yes.
So 4 is much more complex because at least you need to go to 1, right?
That's it.
Which is fairly straightforward. But if you do another one,
right. Now you need to be a bit careful here. You need to put parentheses round.
Indeed.
Because you can't, you have to wrap, the S has to take a complete number. So when you see things in a row in ask, the bracketing is to the left. So we have to put these, so if you just wrote this, the S would be applying only to the s that's in the middle, not the whole of the number made by a successor of 0. So this...
In fact, I think you would think that you have 2 arguments.
Yes. This thing, if you just wrote it without parentheses, would mean this. And that doesn't make any sense, because the s isn't being given a number. It's just being given an s. So we do need these parentheses. So this will take a while to get used to. But okay, we've got to the giddy heights of 2.
It's also taking a while to get to 4 indeed.
Yes.
Let's see.
Yes, so you're going to...
making a mistake.
This is
putting a spade here.
All right, and one more. Yep. So if you hit send,
then what's going to happen? Something bad is going to happen, no?
Then what happens, you can see ask turns the command. So in ask, you solve problems. The problem was define for. And when ask is happy that you've solved the problem, the command turns into a past tense. We have successfully defined for. And you can see 4 is made by 4 is the successor of 3, which is the successor of 2, and so on, all the way down to the 0. So we've built...
Just to be clear what happened, right? Because I wrote code, it was sent, then this is the reply, and now we can accept the reply, and then the reply is going to be pulled over
yes.
the usual box again. Because here you see defined means it's now defined.
Yeah.
We accept, and now it's actually defined in my box.
Right. So when you see a word in ask that begins with a lowercase letter, like 4, those words are common nouns. They stand for something else. So there isn't a whole separate new kind of number called a 4 that isn't made from spuds and lemons. We've said that 4 is defined to be one of the numbers that already existed when we said, we brought those numbers into existence when we made the data declaration to say, this is how you make numbers from Z and S. And there are never going to be any numbers that aren't made that way. And all we've done here is we've given a name to one of the numbers that we happen to like. So I'm fond of 4. Okay. I realize it's peculiar, but we'll get there slowly. I'm going to make another number out of, and I'll go back to using the document camera for a moment. Sorry, Zoom folk. Oops.
You lost this.
So I've got another lemon, and I've got so I've got
I think we can count to 50. No.
Yes. So I'm going to teach Clemens to add.
Oh no.
Yes. Right. So what you've got, you hold the outer potatoes of each of the 2 numbers. When you've got 2 numbers, you might want to add them. Okay. And then the number in your left hand, you can play the game, is it a spud or a lemon? Right?
It's a spud.
It's a spud, which means you can take a step inwards with your left hand. Spud or a lemon?
Spud.
Take a step. Spud or a lemon?
Spud.
Take a step. Spud or a lemon?
Spud.
Take a step. Spud or a lemon?
Lemon.
Okay. So now that you've reached the lemon, what you can do is detach the lemon from the kebab.
Uh-oh.
And then shove the whole other number in its place.
Why do we need the paper?
Because it might get messy. So we've substituted the right number for the left lemon, and that does adding, just literally putting all the potatoes in a row. Okay? And why does adding work? Well, adding wouldn't work if it wasn't the case. In order to make adding work, you have to know you're going to get to the lemon. if you're going to replace the left lemon by the right number, it has to be possible to reach the lemon. So thank goodness there aren't any kind of evil numbers. I'll make an evil thing that's not a number. Let's have something that's not a number.
You would need a circular stick.
Yes, I'd need a circular stick, but in fact, you can do it in a loop.
Triangle loop.
Yes. So if you were playing spud or lemon with this thing, you'd go, oh, spud or lemon, oh, it's a spud, I can take a step. Spud or lemon, it's a spud, I can take a step. Spud or lemon, it's a spud, I can take a step. Spud or lemon, it's a spud, so I can take a step. So this thing hasn't been built by counting, and it doesn't make you the promise that you eventually get to the lemon, so it's a fake number. We don't allow them.
Fake numbers on my research, by the way.
Yes, yes, yes. No, Clemens is that. I mean, these things. It's not that they don't exist; it's that they're not numbers. That things that. Yeah. So we're making to be a number. You have to keep the promise that you eventually get to the lemon, and that's how we compute. Shall we actually define adding? So we've got another box. Right, we're going to first of all define a thing called plus plus. So more ask reading, by the way. Sorry? Yes, switch to PC.
Yes. Good.
Thanks, folks.
It's always good to have Fred in the audience.
Right. So, okay, more ask reading. See that double colon? This the double colon that's here. That's you can read that as saying is a. So earlier we said 4 is a number. And now we're saying plus is a function that takes 2 numbers in and gives 1 number out. So you can read this type. Well, actually, what happens is it takes the first number and it gives you back a function that waits for the second number. And then when it gets the second number, it gives you the answer. So we're saying we're going to define a thing called plus that takes 2 numbers in and gives 1 number out. So now, in order to make this, we first of all have to say, we're going to explain how it is that we're defining plus n and m. So plus is the name of the function, and n and m are standing for the 2 inputs. So we make definitions essentially by writing equations. That's how we get there. But we've got a bit to go first. Remember, so n is going to be the left number, m is the right number, and remember we worked our way along the left number till we got to the lemon. So we are relying on the promise that we can't keep making the left number smaller forever. And the way you pronounce that promise is inductively n. Yeah, and then you hit send. This is send box, send button there. Yes. So that's the way of saying, I am going to make use of the promise that n can't keep getting smaller forever. So it looks like we've not made any progress. But what inductively n is for is to say, I know that I'm allowed to use plus in the definition of itself, provided I use it on something smaller than n. Okay. So the next thing we do is exactly what we did here. We ask, which kind of number are you? So that's from n. I do it there.
Sorry.
We'll fix that in a moment.
Indeed. Nice. Jump line.
So from in ask always says, where did you come from? What made you? What's the and also then what use are you to me? So if you hit send, you'll see we get two subproblems. It splits into two cases. There are two ways of making numbers, 0 and successor. So there are two separate cases we have to worry about. So it's asking us to define what happens when we reach when the first number is 0. And remember, when we got to the lemon, we replaced it with the other number. So we know what's 0 plus m going to be. It's going to be m.
So let's try that then.
Right. Yes. So yeah. Yeah. So it's m.
Yeah. Sorry.
M's look like N.
Oops. Yeah.
Yes. Wow, we have a projector which
tells lies. Right. Well, okay. Let's just rename all the things.
Just Spuds, it's in Netherlands.
Yeah.
Which is not bad usually.
We can just rename all the things. Okay. And okay, you can see that we've done one case. And now we have to think, well, if we're adding successor of x to y, that inductively means we are allowed to add x to something. Because x is smaller than the input we said we were working inductively with. So it's essentially saying, let's carry on adding x to y, but then put the successor back. So you need to write plus xy, and then wrap the whole thing with a successor. Okay? Hit send. Right, and now it's defined. So there are, let's figure out the key ingredients of this. This is an explanation of why this program makes sense. So first of all, we said, we're going to work by making the first number smaller. And it can't keep getting smaller forever. And then we're going to explain case by case, depending on which way the first number was made. If it's 0, we're done. If it's successor, we carry on adding with the smaller input. So some people find that these are recursive equations. You can see that plus is being used in terms of itself. And this makes people nervous. And I think it's absolutely damn right to be nervous about recursive equations. They don't all make sense. Sometimes recursion is nonsense. But here, we've explained why this recursion is not nonsense. Because we are carrying on making the first input smaller and smaller and smaller until we reach 0. Okay, so we can actually just do an example. I think we can say test plus 4 and hit send. And what comes back? 4 stands for successor of successor of successor of successor of 0. So we've just added 4 and 4, and you can see we've computed 8. Okay? Is this, I know it's new and strange, but hopefully you'll get the hang of it. It's pretty ugly writing PLUS in front of the two numbers we want to add. So straight away, I'm going to teach you that we are allowed. If you see something that's made of symbols rather than letters, then you can use it as a two-place operator. So we can write the usual plus sign that we're all used to and have at least something slightly familiar. But the rest of the thing goes the same way. So it's inductively x. We're going to make the first input smaller. You don't need to just hit send.
Okay, I just hit send.
Yeah.
And the backend. No.
Okay. The other thing you'll notice is that anytime a problem splits into subproblems, we make the subproblems slightly more indented. So the spaces at the front are important, and they indicate what's what's a subproblem of what? So, yes. Okay. So if you hit send again, and now you can try testing 4 plus 4. No, you can't. None of this digit business. 4 is still FOUR.
Sorry, I'm not
Yes.
awake. 4 plus 4, indeed.
Yeah, and then hit send,
Send.
and it will compute all the way out.
Yay.
Fabulous. Okay. So you should understand all of the code that gets generated here. I mean, this web page is accessible to you. And you will receive it in the state at the start of the lecture. It's a good idea to reconstruct what happened in the lecture for yourself. And you have the opportunity to do that. We'll certainly also put the code up. Oh, there's something else I should tell you, which is that we have a Microsoft. So the university runs a Microsoft Teams server, and there is a Teams team for CS103. And that's absolutely the best way to get hold of me. I'll tell a story. Say I come from the 1970s, in the middle of the Cold War, and back in the bad old days, the KGB headquarters in Dzerzhinsky Square in Moscow, the KGB guards would wake up the political prisoners every morning with a fresh bucket of cold piss. And that's how I feel when I look at my email. If you send me email, you're pissing in that bucket. So don't, unless you really have to. Because I get so much email, it's just overwhelming. Right, so I'm not saying I don't want to hear from you. I'm saying I actually want to notice when you contact me, and that's why you shouldn't use email. So hit me up on Teams, I'll be around. Okay, so that's another piece of admin ticked off. What else? Let's think about some interesting properties of adding, right? So one of the things that's really important in computing, this kind of seems strange. It's often a really good idea to think through what is the right way of doing nothing. So is there a number that you can add that makes no difference? Exactly, 0. So yeah, so what happens, for example, here we go. I'll back to the document camera. So remember, that's always takes ages to switch. Come on.
Did you really hit it?
I really hit it. There's a notice here which says it sometimes takes up to 15 seconds to switch. And they're thinking about it.
Sometimes even longer, it seems.
Sometimes even longer. What on earth?
Sometimes university systems don't come with a lemon.
Yeah, okay. So, remember, adding, we said, is substituting the right number for the left lemon. What if the left number just is a lemon? Then if I substitute the right number for the left lemon, I'll just get the right number. So adding something to 0 gives you just the something. Yeah? You all know this. I'm making things you know sound strange, but it's a simple thing to check, that there is a way of adding nothing. That doesn't make any difference. Likewise, what happens if the right number is a lemon? Then I follow my adding technology. I work my way along the left number until I get to the left lemon, and then I replace it by a lemon. So it's like nothing's happened, but for a different reason.
And a lot of work happened.
Yes, a lot of work happened to achieve nothing. It's a bit like education. So yes, that's a fine example. It's another fact about adding up for which I will need another number. So somewhere in here.
A few more spots over there, right?
I got some spuds, but yeah, I'm looking for a lemon. Right. So I've got 3 numbers here. Suppose I add them all up. There's 2 ways I can do it. Maybe I'll just make this one a little bit longer. Right? So I can pick the first 2 and add them. So that's 2 and 4 make 6. And then I can add the third. And that's going to get me all the way to 9. I can't get them all on the camera. Well, I can, maybe. Right. So, but I could also put it back the way I started. I could have started at the other end. I could have added the, oops, that was this way. I could have added the 3 to the 4 to get 7, and then added the 2 on the front. And I'd still have got 9. I'm hoping this is not a shock. That, you know, when you add up a bunch of numbers, it doesn't matter what your strategy for adding them up is, it just matters what the numbers are. So, 2 and 4 and 3 makes 9, whether it's 2 and 4 making 6 and then the 3 making the 9, or adding the 4 and the 3 to get 7 and then adding the 2 on the front to get 9. This is good news. This is good news. Anytime you get some useful information about stuff not mattering, that's good news. So it's good that the exact detail of how you bracket up an adding calculation isn't important. In fact, it's very good news in particular because it means if you've got a big list of numbers to add up, you can tear that list in half and give the other half to your pal. Doesn't matter. You know, they could do their half, you could do your half, and you can add the answers at the end, which means you can use multiple processors effectively if it doesn't matter how you group things. So learning about that not mattering is important. So they're simple facts, but they're not casual. It's crucial that adding behaves that way. It's one of the reasons why we like adding. One of the things I should remember to do, by the way, is to hand use gratuitous. I hope you brought writing implements. Can you take one and pass them on? Right, I'm giving you the bits of paper on which I'm hoping you're going to tell me how you use them. Let me get that. Right. So, one thing about the education business is that teachers can be only as effective as their model of their students. So I'd quite like you, what I want you to do on when you get your piece of paper is to write your name and to ask me a question. Or draw a doodle, or tell me a joke, or anything that gives me a clue as to what you're thinking. Okay, so we're close to time, but let's have a go. Maybe I'll do this. Ask, as well as letting you write wee programs.
Wait, we are not on the.
We're not on the.
Okay.
Yeah. Now that we've got our definition, yes, right, I can actually pick this up. So we just I just demonstrated these three equations with potatoes and lemons. Let's see how we do it in ask. Now you should understand that in this lecture, we just invented numbers. And then we invented adding. And now we want to check that these facts which you have known about adding for most of your lives are still true about the kind of adding we just invented. And ask knows nothing about adding beyond the way we defined it. So the first equation, if you look at the definition of adding, that's just true by definition. That was part of the definition. So a strategy that you can use to prove stuff in ask. So again, it presents you a problem and you need to figure out what to do about it. So you replace the question mark with some strategy that makes progress. And one strategy that you can use is simply to say, test this equation by using the definition of the program. So if I say test here, then yes, actually just testing the program by using its defining equations was enough to prove that fact. So prove turns to proven when you've succeeded. However, the other equation, if I try testing that, I don't get anywhere. If you look at the defining equations of plus, to make any computational progress, I need to know whether the first input is 0 or a successor. And if the first input, that's the alarm to tell me to kick out in 5 minutes. Yeah, so because the first input isn't obviously 0 or a successor, that computation is stuck. So testing isn't enough to prove the equation when the zero's on the right. So I'm going to have to make a more interesting explanation of why this equation is true, depending on what exactly x is. And I'm going to need to find out about x, and that explanation is going to follow the structure of the program. So it's going to be written much as the program was. I'm going to say, because when we compute with this x, we're going to recursively make it smaller and smaller. So my explanation is going to have to rely on that getting smaller and smaller and the promise that you eventually get to the lemon. So I'm going to say, I'm going to work just as the program went inductively on the first number. my proof is going to go inductively on the first number, which means I'm allowed to assume the result holds for smaller numbers. So I say, prove x plus 0 is x, and then just like I did in the program, we say from x to find out which way x was made. Was it 0 or a successor? And if I say send, I get two cases back, except I only get the one, right? So if x is 0, then the equation is dead simple. And computation is enough to prove that 0 plus 0 is 0. So ask doesn't even ask me what happens in that situation. On the other hand, in the other case that we do see, we're given that x happens to be successor of something. So when we do from, we get more information. So that's the from strategy. And now there's a definition that helps. The definition of plus will do some work. So now if I say test, then actually that's the proof done, because what happens is that the computation takes one step, and I get that the left-hand side turns into that thing. So after one step of computation, a successor bubbles out the front, and two successors are equal if the numbers one less are equal. So so 3 plus 0 is 3 because they're both because 2 plus 0 is 2, and then you add one more on each side. So the goal about the larger number reduces to the same problem about smaller numbers. So the inductive explanation is saying that we can solve the large problem because the smaller problem is already given to us. That's what inductively is meaning here, is that we're going to work by making that number smaller and smaller until we eventually get to 0. So we're building up the explanation of why x plus 0 is x, the same way we built up the number x in the first place. So 0 plus 0 is 0, and because of that, 1 plus 0 is 1, and because of that, 2 plus 0 is 2, and so on. All right. So one of the things about this setup here is that you folk stay put, and we bugger off. So I'm going to need you to scribble a wee bit of feedback on your bits of paper and pass them in this direction, please. Meanwhile, I will stop the recording.
What will happen next? Is it 106?
104 is next.